Previously, we had talked about discrete probability distributions, and so that was, we've determined using counting techniques the number of ways an event could happen divided by the total number of possible outcomes, and that required us to learn those different methods for counting how the different outcomes of an experiment. Not all experiments are easy to count, and we looked at a couple that kind of emphasize that point. Now then we want to talk about continuous probability distributions, and you then might guess that a continuous distribution is associated with a random variable that's continuous. All right, and so it's a little different here because now we don't have a probability associated with a single value of the random variable like we did in a discrete distribution. What we look at are intervals of random variables, and so our notation here, a little bit different. We use a function f of y to denote a probability density function, and this is referred to as a PDF quite often in statistical literature. All right, and so this applies to a continuous random variable. And properties of a PDF or a probability density function the function is non-negative, and that the area under the curve and above the horizontal axis is 1. And we tend to draw things in a first quadrant here. But when we look at our probability density function, f of y, on the vertical axis, so what things are saying here is that we have a curve for f of y, all right? The area under this curve and above the horizontal axis, this area is equal to 1. Okay, and that this function then, it can touch that horizontal axis here, but it can't go below it. Okay, so those are two of the properties then for these continuous distribution functions or density functions. Okay, so different from what we saw in discrete density, with a discrete probability distribution, is that the probability of a continuous random variable y achieving a single value is equal to 0. So the idea is that probability, you have this y-axis or horizontal axis, you have the PDF curve above it, and this value of a, all right? The probability is going to be associated with area. And so the reason that this is equal to 0 is that there is no area over a single point. Okay, and so that is why the probability that y achieving a single value is 0. Okay. I'm careful here with my grouping symbols. Okay, here I have the probability expression. So here I have an interval under the curve. I have some values a and b that are different from each other. And this probability is here, the area in between these two. So area, it's just saying that the area between a and b, above the horizontal axis, and underneath the f of y PDF, that's an area, and so that this area is always non-negative, of course. Okay, and this is, and more specifically, whether we put things in terms of strict inequalities or allow for equality here, less than or equal to in these cases. We're looking at the area under f of y between a and b. So that's the picture really then still applies here. Given that the probability associated with a single value is equal to 0 and that we have these areas, then that means I can write a probability statement such as this where a and b are excluded here. So strictly greater than a and strictly less than b for these values of y. That probability would be the same as the interval that included, let's say, a, or a strictly less than y, but y could be less than or equal to b, or you could have both of the expressions here be less than or equal to. So a less than or equal to y, y is less than or equal to b. All right, so picking up a single point, or in this case 2 points, doesn't change the area because the area over a point is 0. Now that's much different than what we talked about last time. Remember when we looked at some of those questions, and we had, I think in one of our examples we talked about more than 18 or at least 18, those kinds of things. Whether or not you picked up that endpoint, it made a difference in the probability calculation with a discrete random variable. Here it does not. All right, suppose I just have the simple function here that the function f of y is equal to 1/5 on an interval from 0 to 5 and 0 otherwise. So what we're looking at then in terms of a number line here, or set up a coordinate system at 0, 1, 2, 3, 4, cut it off a little soon, 5, and we're at a height of 1/5. So this says that the function f of y is at this height of 1/5 when y equals 0 all the way over to 5. From 5 and to the right, it's at 0. From 0 to the left, not including the endpoint 0, it's the function is equal to 0. This satisfies the conditions of the PDF, the first condition, in that the function is non-negative everywhere. Okay? Is the area 1? Is the total area under the curve and above the horizontal axis equal to 1? Well, yeah, real simply here, what is that? We have this area in here. All right, we have a rectangle of length 5 and height 1/5. Length times width is 1. That's easy to figure that area, right? So this does satisfy the two conditions then that we named back here. Non-negative function, and that the total area is equal to 1. All right, so very simply then, when we want to talk about the probability and we want to look at y on the interval 1 to 3, okay, you could real quickly go back through this. 1, 2, 3, 4, and 5. We're up here at a height of 1/5 again for the function. We're on the interval 1 to 3. So what's the area of this smaller rectangle here? All right, well, that's easy. This is of length 2, height 1, and so here, our height is 1/5. The length of the rectangle is equal to 2, so our probability is 2/5 or 0.4. Y strictly less than 4? For most of the things that we're looking at, the PDF's not going to get too complicated. There's our function again, and what we're looking for. If y is strictly less than 4, then the area we're looking for is here, plus the zeros piece, right? And so we end up with 0 plus the probability that y, put an endpoint of 0 here, less than or equal to y, less than or equal to 4. Could be strictly less than 4 or less than or equal to, so it's 0 plus the length of this is 4, the height is 1/5. 4/5 or 0.8. So just emphasizing that we recognize that values over here were in the probability statement, but they had probability 0 of occurring. Sorry about my... On probability that y is between -1 and +2. drawing f of y again. So we're looking at -1 to 0, and then from 0 to +2. So 0 plus 2 times the height of the curve, which is consistently 1/5. Again, 2/5. We're looking at the same probability as the one directly above it, but we're looking at different areas under the curve. Logical and here, so that y is in the closed interval 0 to 4 and in the closed interval 3 to 7. All right, so what we're looking for, logical and means both must be true, right? Okay, in the closed interval 0 to 4, that 1, 2, 3, 4, we're looking for everything here and to the left, down to 0, 3 to 7, okay, we're looking for this part to the right here, and then the 0 interval here. So what we need is logical and means both must be true, so it's that intersection. Okay, and so that's just a distance of 1 and height 1/5, so we come up with that probability is 1/5 for both those conditions to be true. Logical or means either one or both. In this case, the ones I picked, two of our earlier, this condition, I guess we didn't have a greater than or equal to 4. -1 over to 2, greater than or equal to 4 in the second one. So we're looking at this piece here. We pick up another 0 bit down below. So either of those are true, so it's either here or here. There is no both to subtract, right? Remember we talked about or last time. Events A or B, the probability of event A plus the probability of event B minus the probability they both can happen. There is no overlap here in this case. All right, so for us it's this 2/5 plus this 1/5. And if you wanted to note that you're accounting for all the pieces, you've got a 0 here and a 0 here. So this probability is 3/5. So if all of our PDFs are a uniform function, we're good. Area of a rectangle, right? Doesn't happen that way, unfortunately. Okay, but you get the idea. So what I wanted to do was just really to kind of talk about the probability statements. Clearly figuring the area of a rectangle is not hard. All right. The thing is that most of the PDFs we work with aren't uniform distributions. So like the discrete uniform where everything had the same probability, there's a continuous uniform where that function just stays at the same height over a selected interval. Okay, we want to talk about the normal distribution, and you may have heard the terminology a bell-shaped curve. We still use our population parameters mu to cite the location and sigma squared to cite the width or scale of the distribution. And so if I have it's supposed to be symmetric. Sorry about that. I got a lump on the right side. Okay, it's supposed to be symmetric. All right, so the idea here is right here in the middle, we have our value of mu. It is symmetric, so mu is also equal to the median. All right, meaning that the area over here is 0.5 and the area over here is 0.5 if it's the median, right? So we could write 0.5 for the area. 0.5 is the area here. Total area is 1. All right. And so that if we have the value of mu changing, just to kind of picks this distribution up and moves it along the number line somewhere, keeps that same shape. If we have another distribution with the same mean, and I'm sure the idea is that they're supposed to have the same area, but I'm doubtful drawing it that well, okay? But if you have the second distribution has the same mean, so we could look at this as saying that our first mean is equal to our second mean. Here, this is our second population, population 2, with the dotted green curve, population 1 with the solid red. All right, if we were to compare the variances for these, this population 1 would have a variance of sigma 1 squared, and how it would compare to the variance for population 2. Which one of these distributions has more spread? Population 1. Population 1 has more spread in it. The areas are both 1, and so that implies that the variance of population 1 is larger than the variance of population 2. Okay, we would have, if the variances were exactly the same and the means were different, then we could have either the solid, whichever distribution it is, say this solid red distribution with mu 1. If we had a third population and had a mu 3, but the same variance, it would be moved over wherever and centered at the value of mu 3. Does that make sense? Again, the total area under the normal curve is 1. My illustrations probably don't suggest that these two are the same, but if we were drawing the actual function, they would be. Okay? So we go back to our definition for the interval here. The probability that y is between two specified values, a and b, is given by our normal curve here. Find out where a and b are, and find the area under that curve, just as we did with the uniform distribution previously. All right? I've already marked it up here. This area to the left of the mean is equal to 0.5. The area to the right is equal to 0.5. And so what this means is that we have a distribution that is, we are symmetric about mu, and by that symmetry is why we have those 0.5s. We haven't talked about what the value or the expression for f of y is yet. We will. Cumulative probability, whether we're talking about a discrete distribution or a continuous distribution, a cumulative probability is the probability that y is less than or equal to some value a. Okay, so the cumulative probabilities are always involved less than or equal to. And so if you want to shade something in a picture, you're always shading, for you guys, shading the left-hand side of the image for the area in question. Okay? Cumulative probability functions in literature are denoted by capital F. The PDF, the probability density function, is F. And so cumulative probability functions, capital F, as y gets larger, the capital F of y gets close to 1, since probabilities cannot exceed 1. All right. For the normal density curve, this is the function here. Notice it is a function of both mu and sigma. We've got sigma down here, sigma squared up here in the exponent. And then, our mean value for mu is centered here. Values of y then range anywhere in the real numbers or from negative infinity to positive infinity. If we say that y has a normal distribution, this is our notation for saying that. Y is distributed normally with a mean mu and a variance sigma squared. It is always the case that mu is listed first, or the mean is specified first, and the variance is second. So when you see numbers in those positions, the first number is always mu, the second number is always variance. Okay? Now then, if we were to take this function and we were to draw it, it should be that bell-shaped curve I've been trying to draw here for the last couple of pages, right? That's what this function f of y looks like. To check that it's a PDF, you can compute for any value of y. This is a positive function, and if you wanted to check that the area under the curve is 1, how would you do that? Not everybody can answer this question. It requires calculus. All right? But if you wanted to check this, calc students, you would take and you'd integrate from negative infinity to positive infinity this function f of y. And you check that the area under that curve is 1. Verifying that for a normal density function involves a change to polar coordinates and a substitution or two. Okay, so it's not real straightforward. Okay. So then our question then is if we have that y is distributed normally about a mean of mu and a variance of sigma squared, how do we find the probability that y is in some interval a to b? All right, modifying this, so notation here for calculus, students with a calculus background, you're integrating from a to b the function f of y with respect to y. Calculus is not a prerequisite for this course, all right? But what that generates for us is the area under f of y between a and b. Okay, so what we're going no, you don't need to know any calculus, all right? For those that do, I just put it in there to kind of help fill in some of the gaps, all right? So we want to be able to figure out what this area under the curve is. So let's back things up a little bit and not talk about every possible normal distribution, but let's just talk about one in particular. So the normal distribution we're going to start with here is referred to as a standard normal. And the standard normal reference tables gives us probabilities associated with a normal random variable that has a mean of mu and a variance of 1. Our textbook and most textbooks use a z to denote that a standard normal random variable. And so the notation then is z is distributed normally about a mean of 0 with variance 1. Okay, or shorthand where it's normal 0, 1. Okay. There's a standard normal reference table in your text. Let's see. Table A1, I believe. I have page 721, ranging through 726. Okay, and on screen is third edition of the book. All right, it gives us these values for z and the probability for being greater than the stated value of z. These values of z begin at negative 3.99, too small to be seen. All right, and then goes down this direction, they increase, goes to the top of the next column and so forth. And then as you keep going across, so now I'm on page 723 for this side here. Can't get the page number in at the same time. Notice we're moving up in the values here, and at the go over to page 724. We have positive z-scores. So what this is doing is these probabilities, how do they compare? The probability greater than z. Let's back up, find 0. Page 723. A value of z equals 0. It's right here. Okay. The probability of being greater than 0 is 0.5. Okay. That one we already knew. just by the symmetry of the function, right? Okay. And so that as we get values of z that are larger, this probability decreases. Okay. So what the table gives you, so this is in our Brian Wilson and Moore. We're on page 721 through 726. Excuse me. This is table A1. Now, if on the top of page 721 you drew a picture like this, we're graphing z. Oh, sorry, thank you. Forgot I zoomed in. All right. If you wanted to draw this like at the top of page 721, what it's giving you then is a value for z here, and the probability greater than z is the right-hand area. Now, I point that out because in some other references, they may not give you right-hand area. Some references give left-hand area. Some references give the area between 0 and the score. And so the picture changes. All right, so our textbook is set up for right-hand areas. Guess I don't need the extra z in there. So keep that reference table open. You need to bring your textbooks to class with you every day because this is just one of many tables we'll be using. Okay? So we'll just go through some exercises learning how to read this table. So use the standard normal reference table to find the following probabilities. So the probability that z is greater than 1.17. Okay, so the z distribution has a mean of 0. Okay, 1.17 then has to be to the right of that. And so this says we're looking for the area to the right of 1.17. We're looking for this bit over here. All right, so our common sense check is that we know this answer has to be smaller than 0.5, right? Because the area from 0 and to the right is exactly 0.5. Okay, so look up the value of the z-score of 1.17 in table A1 and tell me what you find. .1210. Does everyone locate that? Okay, that is exactly this probability because the table is set up to give you right-hand areas, and that's the probability being requested. What's the probability that z is strictly less than 2.10? Drawing z. 2.10 is over here. We want the probability that z is less than that, so we want this large shaded area. Okay, so the table's going to give me what? If I look up a z-score of 2.10, that number that I get is right-hand area. Okay, so how do I find left-hand area? Subtract from 1. Right? This is the complementary event to what the table is set up to give you. All right? So this would be equal to 1 minus what value do you find in the table? 0.0179. Does everyone agree? All right? And so that this probability, notice we've shaded most of the area under the curve, right? And this is equal to 0.9821. Okay. Find the probability that the standard normal score Z is between -1 and positive 0.5. So how would you do this? The area from -1 and to the right is the bigger piece, okay, that the table gives us. So if we look up a z-score of -1, what area do we have for the right-hand area associated with -1? .8413. Okay, if that's the area from -1 and to the right, we subtract off this area from positive 0.5 and to the right. So what's the right-hand area or tabled value given for z equals 0.5? .3085, do you agree? And the difference between those? Then I have 0.5328. What's the probability that Z is between positive 2 and 2.53? Would you go through the same sort of process that we did up here? Agreed? And we know it's going to be small. So clearly my scale here on the horizontal axis is not exactly correct, is it? For a 0.03 difference in Z. So you look up the Z-score associated with positive 2, the probability associated with the Z-score of positive 2. At 0.0228 for this area, this direction, and then from here over, we're subtracting off 2.53. I misspoke. I said a difference of 0.03 is 0.53. I have 0.0057. And the difference between those then is 0.0171. Everybody comfortable with that? So, yep. Hopefully you get it. So if you're as comfortable as you can say, I know this forwards and backwards, I'm good. Okay? So the next question is, well, then do it backwards. If you know the probability, what's the z-score? So if we know that z greater than a, the right-hand area is 0.05, what is a? So this means our picture if the right-hand area is 0.05, with respect to 0, where is the value of a? To the right or to the left? Has to be to the right, doesn't it? Okay? Because if I put it to the left, I know the area from here over is 0.5. The area we're looking for is 0.05, smaller. All right, so a has to be over here because this area is 0.05. All right? So how do we determine A? Now we go to the table, and instead of looking in the column for Z, look in the column for 0.05 and find the corresponding value for A. And that one's going to be a little trickier because you may not find that probability exactly. Okay? So if you go to the table and look up the probability greater than z or right-hand area of 0.05, what do you get? .64 has a right-hand area of 0.0505. 1.65 has a right-hand area of 0.0495. And we're right smack in between those. Almost everywhere else, I don't worry about interpolating. This is the one place where I tend to. All right. So here I'd say that our value is 1.645. We're halfway in between. Does everyone agree? All right. If the right-hand area is equal to 0.8, what is the value for A? Okay, where is A with respect to 0? To the right or to the left? Yep, to the right, to the left. Sounds like we're dancing. Which one is it? The area from 0 and to the right is 0.5. So if the area I'm looking for is 0.8, then A has to be, it's a right-hand area, isn't it? Okay, so if I put A over here, it's going to be this 0.5 plus 0.3 over here, right? So now then this area to the right of A is indeed 0.80. All right, so I go again to the probability column and find the value of 0.8. Probabilities have to be positive. I was about to misspeak there. All right. If we're not exactly in the middle like we were in the previous illustration, pick the one that's closest. If we need to know it to if we need to know it to another decimal place for specificity, we can get that in other means. Right now, just take the closer one. Okay? So what is your value for what is your value for A? Negative 0.84. Does everyone agree? The actual area listed in the table is 0.7995. The closest area, right, to 0.8. So draw the picture. I know we're all grad students and we don't think we need to draw the picture, but if it helps you get in the right half of the distribution, draw the picture. Okay? A lot of people think I don't need to draw that, but it would help sometimes if you did. All right. Probability that Z is strictly less than A is equal to 0.9. So draw the picture. Where is A with respect to 0? Okay, it says Z less than A, so that means left side area is 0.9. So if we're going to the left, from here over is 0.5, so A has to be over here, and that this area to the left is 0.90. So again, in the probability column, we want to look up what? Well, if the area to the right is 0.9, if the area to the left is 0.9, the area to the right is what? 0.1, because total area is 1. Okay? I need to know right-hand area to use this table. All right, so I look up an area of 0.1 or probability 0.1 and find the associated z-score. What value for A do you find? I have 1.28. Do you agree? Okay, it's not going to be negative because we marked it to the right of 0. Now, what is the right-hand area associated with negative 1.28? You raise an important point. If you look up negative 1.28 for Z, the area to the right is 0.8997, or roughly 0.9. So if you're over here at negative 1.28, the right-hand area is 0.9, but we're looking for left-hand area. Okay, and so that happens by symmetry of the normal distribution. That's why we see that. Okay, but that's also, again, why we draw in the picture, make sure we're staying in the right part of the distribution. What other term have we used this week that describes this value? A would also be what? The probability of being less than that score is 0.9, so A is the 90th percentile, right? And so A equals positive 1.28. Is the 90th percentile. What could we say about these two up here in terms of percentile? In the first one, 1.645 is the area to the right is 0.05, the area to the left is 0.95. So up here, 1.645 is the 95th percentile of the standard normal distribution. 3 nods. Okay. And this one, A equals negative 0.84. So percentile, remember, then that's got to be cumulative probability or left-hand area. Okay. So here, negative 0.84 is the 20th percentile of the standard normal distribution. You agree? All right, here we want to find a value of A such that negative A up to positive A, that area is equal to 0.99. So here we're kind of looking for, you want to think about this, the middle, 99% of the data. So we want to find minus A, same distance over, plus A. They should have been the same size, but all right. So we're looking for this area in between these two to be 0.99. How do we do that? Well, if the middle area is 0.99 and it's symmetric, despite what my picture looks like, all right, and the normal curve is symmetric, then that means then that this area is equal to what? Well, 0.99, that means I have 0.01 left over, and I have to divide that evenly between the two ends that are the same size. So that means this piece is 0.005, and this piece is 0.005. Those three pieces together add up to 1. So what do I look up? I go to the probability column, find the value as close to 0.005 as I can, read the z-score, that's A. Then the negative A then determines this point. So what is the value of A that determines the middle 99%? This is probably the other case where we could look at things and interpolate 2.57 or 2.58, you may say, or if you pick 2.575. Those are the three possibles that I would accept as a correct answer. 2.5-ish is not close enough. All right, I'm looking for the closest one. Okay, now do we know what forwards and backwards? Backwards is a little harder than forward, maybe. All right. One of the things we talked about last time was the empirical rule. Empirical rule means what? Well, here, we have a standard normal distribution. So that means the variance is 1, the standard deviation is 1. So the value of z is how many standard deviations away from the mean we are, isn't it? Okay, so we had a result that said that in the empirical rule, approximately 68% of the data is within one standard deviation. How could we verify that here? Could we? So I don't have it written on any one of the sheets before. So kind of the thing what we're checking here is what's the probability of seeing a z-score in between -1 and +1? Because that would be within one standard deviation of the mean of 0, wouldn't it? What's that probability from our z-table? We hope it's close to 0.68 by the empirical rule. How close is it? If you look up a z-score of 1, you get the right-hand area. That's this piece. What's the probability of associated with a z-score of 1? .1587. Okay, what's the probability of a z-score associated with -1? So the area from here to the right. Is 0.8413. We had that one in one of the first ones we did. And so the difference between these is what? 0.6826. Approximately 68% of the area is within one standard deviation. Up above here, the last case we did is with roughly 2.5 standard deviations. We had 99% of the data. Empirical rules said all or almost all of the data within 3 standard deviations, right? We're not saying anything contrary to that, are we? We could do the same thing with the area between z equals -2 and +2, right? What should it be close to? Should be close to 95%, right? Or 0.95. So you could verify that one also. All right, so empirical rule says this should be close to 0.95. Do we need to go through it, or are you okay with it? What does no answer mean? Or yes to an either or question? Okay. So +2, -2. What's this area for z equals +2? At 0.0228 from -2 all the way to the right. .9772. Whoops. About a 2 there. 0.0228. And the difference is approximately 0.95. Well, all right. Empirical rule makes sense. Okay, we have to recognize then that the z-score, pardon me, I got a glare there. The z-score is the number of standard deviations away from the mean. The sign of the z-score is, are you to the left of the mean or to the right? Okay. How else could we have done that? Rather than this difference, we could have taken, this total area is 1, we could have taken 1 minus 0.0228 minus 0.0228 to account for this side. By symmetry, I know this piece has to be 0.0228 also. All right, so I could have taken those two things together, add those together, and subtract them from 1. That would have been the other way to do it, rather than the big piece minus the little piece. Well, that's great if all of our data is distributed according to a standard normal distribution. So all we have to do is make sure all of our data has the mean of 0 and variance of 1, and we're set. Right? Okay? Doesn't quite work that way. So what if our probability distribution is not normal 0, 1? What if it's not standard normal? How do I get those probabilities? Okay? And so what we do is use this transformation of z. So this we take the value of y in question, we subtract its mean from it, the mean of the population distribution from y, and divide by the standard deviation. All right, and that's referred to as a standard normal transformation. So what's going on here is that you have your data centered over here at some non-zero value mu. Let's say it's a you have this distribution determined by sigma. So this is your distribution for y. You take each of these values for y and you subtract mu from it. So that really kind of takes this whole distribution, picks it up and moves it over and sets it down at 0. Okay, so every point along here, all that does is just move the thing over. What changes the shape of it is dividing by sigma. So that the shape change of it and then achieves the standard normal. Just moving it over just makes the mean 0. Dividing by the standard deviation changes it. So that's what this transformation does, is it creates this normal 0, 1 here. So if I can take any distribution and transform it to normal 0, 1, then I can answer the probability question. Does that make sense? Okay, so suppose we have a normal population with a mean of 30 and a standard deviation of 4 that we've sampled. We want to find the probability of a observed random variable, a value of random variable y that's greater than or equal to 33. Okay, so we have that our y's are distributed normally with a mean of 30. Standard deviation is 4, so variance is, I'll write it as 4 squared. Okay. Find the probability that y is greater than or equal to 33. So what we're looking for, when we talk about y, the distribution of y is centered at 30. Okay, and 33 is to the right of that. And we want y greater than or equal to 33. We want right-hand area. Okay, so we take this probability statement here, probability, transform it, y minus mu over sigma, greater than or equal to 33 minus 30, the mean, divided by sigma, which is 4. So be attentive to whether you're given standard deviation or variance, so you divide by the right thing. All right. This transformation here, this is a z-score, so this is equal to the probability that random variable z is greater than or equal to, this would be 3/4 or 0.75. So then we can look up the z-score of 0.75 in table A1 and report the right-hand area. So for z equals positive 0.75, what do you find? Right, 0.2266. All right, our common sense check, the best we can tell here is that it's going to be smaller than 0.5, right? Do I have to redraw the picture for z? It's going to look exactly like this, except this will be a 0, this will be a 0.75, and that would be a z. So I could either draw the picture for y or draw the picture for z. It doesn't matter which. Right? We're still looking for this same right-hand area. What's the probability that y is less than or equal to 31? Mark the mean of 30. 31 is here, and we're looking for left area associated with y. So this would be the probability y minus mu over sigma less than or equal to y is 31, mu is 30, sigma is 4. So we're looking for the probability of a standard normal score z being less than or equal to what? Positive 0.25 or 1/4. How do we find that from the table? We look up z equals 0.25, find the right-hand area, and we have to subtract it from 1, agreed? So this would be equal to 1 minus, what area do you find? 0.4013. Subtract that from 1. And so that we end up with a probability of 0.5987. Agreed? Common sense check. We knew it had to be bigger than 0.5, right? What's the probability of seeing a value for a random variable y between 17 and 32? I'm looking for this area. We need to transform both 17 and 32 to standard normal scores. So we have 17 minus 30 over 4 less than or equal to, I repeat the formula here in the middle, 32 minus 30 over 4 on the right. 17 minus 30 divided by 4. A negative 3.25. Less than or equal to z. Less than or equal to positive 0.5. Now be careful. A common mistake that could have been made in any one of these that happens to students, if they compute z and z ends up between 0 and 1, very often that gets confused for the probability, and they'll report the z score for the probability, and you're not there yet. Okay, just a caution. All right, so we have to do what here? Look up the right-hand area associated with negative 3.25 and the right-hand area associated with positive 0.5, and take the difference between the two pieces. Agreed? Negative 3.25 determines the right-hand area of 0.9994. Positive 0.5 determines a right-hand area of 0.3085, and the difference between those I have is 0.6909. Do you agree? Any questions over transformation? So given a value for y, we can transform it to z. Okay? Now, backwards, like we did with z. Between what two values does the middle 95% of the data lie? All right, so what we're trying to find then, the middle 95%, so we're going to go forward and backward the same distance, but we have a y1 on the left and a y2 on the right. We want to find out what values of y1 and y2 we need. So I'm going to take that y off of the top of there. We still have our distribution, just to bring that information forward, that y is distributed normally about 30 with a variance of 4 squared. All right, so our probability statement is that the probability that y1 is less than or equal to capital Y, less than or equal to y2, that's equal to 0.95. Okay, so how do we do that? So if this is 0.95, how big is this piece? 0.025? How do you know? One minus the 0.95 is 0.05. I've got two pieces left over that are split evenly. And so that 0.05 divided evenly is 0.025. And so this one is also 0.025. So now that I have all the areas accounted for, what z's do I look? How do I look up z? Okay, so I could draw exactly the same picture right here. This top line here, this is for the y's. If I change things over to z, I'm going to do is just change the axis right below it. 30 is going to correspond to the mean of 0. I need a z1 and a z2, don't I? How do I get those? Well, the easiest one is probably over here. Look up a right-hand area, 0.025, and find the value of z that determines that. All right, so in the probability column, find 0.025. That's associated with a z-score of 1.96. All right, so z2 must be positive 1.96. How do we find z1? A couple of different ways. You could look for a probability, a right-hand probability of 0.975, taking the 0.95, adding to it the 0.025. And you could find a probability 0.975 to define z1, or by symmetry of the z distribution, standard normal distribution. If this is positive 1.96, that determines 0.025 in the right-hand area, what is the value of z1 that determines 0.025 in the left-hand area? Negative 1.96, exactly. So if you use the 0.975 approach, if you want to just take a second and check your table, you'll also get negative 1.96. Okay? What do I do with those pieces of information? I don't need to redraw the picture. It's the same picture. It's just the axis that changed. Okay? So our formula then is that we had, let's say, z1 corresponds to y1, and y1 is y1 minus mean 30 divided by 4. And this z1 now is negative 1.96. Similarly, over here we could do y2 minus 30 divided by 4. That y2 corresponds to z2, which we've just determined is positive 1.96. And we can solve these two expressions for y1 and y2 respectively. All right, so over here on the left in purple, 1.96 equal to y1 minus 30 over 4. We would end up with y1 equals 30 minus 1.96 times 4. That negative sign here is why we're subtracting. I have positive 22.16, a value smaller than 30. It had to be, right? And over here on the right in red, y2 would be equal to 30 plus 1.96 times 4. $37.84. You agree? And just as a quick check of your arithmetic, you could check then that this difference, 37, this is 7.84 units above the mean. This one is 7.84 units below the mean. They have to be if it's middle, right? It's symmetric. They're both the same distance from 30. Find the 95th percentile of this normal 30-16 distribution. So that means we need to find a value we'll call y with subscript 0, or y as red as not, y naught is less than or equal to is the operator here. So the value random variable y less than or equal to y naught is equal to 0.95. That's what it means to be a 95th percentile, right? And so the value for y naught is to the right of 30, agreed? And this right-hand area, if this is 0.95 to the left, the right-hand area must be 0.05. Okay, that's for y. So correspondingly for z, the mean is 0, and the corresponding value for z naught that determines a right-hand area of 0.05 is what? Does everybody understand what I'm doing when I draw these two different scales down here? So I don't have to redraw the whole curve. But it also hopefully helps get you accustomed to the idea that mu translates to 0 and that. Okay, so y naught, we need to know the z naught value so we can figure out what y naught is. What is the value for z naught? Excuse me. You're off a decimal place here. You want 0.05. You went 0.005, I think. It's at 1.645. Oops. Does everyone agree with that? Yeah, when I write a leading 0 up there, that the decimal points aren't always seen, so that's one of the reasons. Try to emphasize it. All right, so what do I do with this now? 1.645 is the 95th percentile of standard normal, but it's not the 95th percentile of y, the y distribution. All right, so that means I have to grab that transformation formula, and I'd have 1.645 would be equal to the value for y naught minus 30 divided by 4. The y naught is equal to 30 plus 1.645 times 4. And the 95th percentile then of this distribution of y is equal to 36.58. Do you agree?